Hello, and welcome back to the GoEngineer YouTube channel. My name is Jeff Linderman, and I'm a Senior Specialist for GoEngineer with over 30 years experience in the injection molding industry. Please hit the subscribe button to subscribe to our YouTube channel if you haven't already. But in this 30-minute webinar, I will briefly cover the plastics matrix and the simulation study workflow, and then dive into some of the results from an analysis to interpret them and make changes to our model design or process settings. I'll cover some of the fill, pack, cool, and warp results. First off is our plastics matrix. SOLIDWORKS Plastics has 3 levels: Plastics Standard, Plastics Professional, and Plastics Premium. Plastics Standard has only the filling phase of the injection molding process. Plastics Professional adds the packing phase to the process. And Plastics Premium is where we get our cool and warp analysis. So Plastics Standard is geared toward your part designer. Plastics Pro is geared more toward when you're starting mold design, and then Premium is the full package with a 3D CFD cooling analysis of your cooling channels in the mold, and then your warpage analysis of when the part comes out of the mold and sits on the table and finishes cooling. So the SOLIDWORKS Plastics workflow, the way it works is we start with a model inside of SOLIDWORKS. The SOLIDWORKS Plastics is an add-in in SOLIDWORKS, so you're using the SOLIDWORKS user interface. Once we have our model, we create a new study. The next step would be to assign a material out of the material library that's provided. There's over 4,000 materials in our library. And then any process settings we need to change or set, we can do that here as well. There are default settings that the system will pick up from the material that we chose, such as melt temperature and mold temperature. So we don't have to know the injection molding settings for the process, right? We can just use the default values. Next, we assign our boundary conditions. This is our injection location or our clamp force direction. If we're doing a venting analysis or we have a hot runner system, we can do a filled hot runner system in there as well. Typically, your injection location and the clamp force direction are what you're going to be using most in the analysis. Then we mesh the part. The mesh applied to the model, runner system, cooling channels, and a virtual mold. Once we do that, then we can run the analysis. And once the analysis finishes, then we have our results. So this is what we're going to concentrate on today is the results. We're not going to actually go through all of the steps, but I just wanted to give a good overview of the actual workflow. And at any point, we can go to any of these and change the settings. So once we create the study, we can make any changes or duplicate the study and create a new study as well. So let's look at some fill results. What we're going to look at is the fill time. We'll look at areas of air traps, weld lines, the sink marks in a part, the cooling time, and pressures as well. So the first studies that I run here are run with a shell mesh, and we can select the ISO surface clipping plane options, which is going to put these waves basically on the surface of the part. The more distance between them is the slower the fill happens. So if we look at this, the areas with slower fill are going to have more space between the lines. And we can see from the filling animation, as it flows around this area, it's race tracking around the outer edges of the part. And that race tracking is going to cause air traps. So if I turn on the air trap, I can see these magenta ball areas that are showing where air traps are going to occur. So these air traps that are in this wall are due to that race tracking. So this could cause burn marks, which is superheating the trapped air with the molten plastic, and under pressure it doesn't have anywhere to go, and it basically burned the plastic, as in this image I have down here. Weld line view is going to show areas where multiple flow fronts meet on our part. In this case, the flow front splits due to the race tracking, and there's also a few weld lines that happen around the small openings down at the bottom of the part. This weld line probably going to be an issue, so we definitely need to make some changes to get rid of that race tracking and also get rid of the weld line. The weld lines in SOLIDWORKS Plastics are showing the angle of the flow front velocity vectors. So A wide angle is going to yield a stronger weld line. So the more flat the flow, you're going to get a stronger weld line. A steeper angle, you're going to have a weaker weld line. It may lead to part defects, possible part cracking, or failure around the weld line. Another result to consider when looking at weld lines is our flow front temperature. If the temperature is low or close to the glass transition temperature of the polymer around a weld line, polymer molecules would not bond well, and that's going to create a weak area in the part as well. So if we look at the section view of this model, we're looking at why we have the race tracking, right? It's showing that the wall thickness of the label recess that we have here is not uniform with the rest of the part. So the flow of the plastic's having trouble getting through this thin wall section. It's a good practice to have uniform wall thicknesses in an injection molding part. So what we can do, we can move our label recess feature before our shell feature, and then it's going to create a new wall thickness in this area so it's more uniform. It just creates another little step on the inside of the part, but we have a uniform wall thickness, and we'll see what results we get out of that. So the duplicate study command that we have in SOLIDWORKS Plastics allows me to make changes to the part or changes to any settings or anything that I want to do. So these changes that are needed are going to create a new configuration of our part when we do a duplicate study. So just like anything else in SOLIDWORKS, when you have a configuration, any changes I make to the configuration, I can have it not change the original. So then we're not going to lose our original study data. We're copying it and then starting with a new study. Basically, any changes to the model need to be remeshed to capture the new geometry, and then we can run the study again. So once I've done that, I ran the new study, and here we can see our injection pressure result on the left. This was the original one, so our injection pressure was over 98 megapascal. And then on the right, we can see with the new, more uniform wall thickness, it's 87 megapascal. So our max pressure is lower, and we also see it's more uniform across the part. Our fill time animation plot, it's going to show a more uniform flow across the part. We don't have the race tracking anymore, so it's definitely solved our problem with that. This fill time plot is run with a solid mesh versus the shell mesh, so it allows us to see the internal areas of the model, not just the surface. Cooling time, this I feel is one of the most important results to look at when you're using plastics standard and as a part designer. The cooling time is the longest part of the injection molding cycle, so the result lets us see areas that take the longest to cool. If we can reduce the cooling time, then we're reducing the cycle and we're saving us money. With a solid mesh in the clipping plane mode, I can turn on the clipping plane, and this one I have it clipped through two planes. I can see internal areas in the part. Identifying the areas and making design changes are going to reduce the cooling time, which reduces the cycle. And like I said, it's going to save you on part cost. Our sink mark result, it's going to identify areas where sink marks will occur in the part. The sink mark will appear as a dimple or a depression in the part surface on the actual molded part. Having them in a cosmetic area of the part would not be acceptable in most cases. Well, the sink marks occur due to the thick wall sections, usually around a rib or a boss in the part. So these thick sections will take longer to cool and also have higher shrinkage, which is what creates the sink mark. Now we'll look at some of the pack results as well. So the pack analysis in SOLIDWORKS Plastics Professional allows us to determine an effective packing time. This is essentially the time at which the gate freezes off and no more plastic can be pushed into the part cavity. The temperature results are going to reveal the temperature of the part at the end of pack and at the time of ejection from the mold. Our pressure at end of pack is going to show areas where packing pressures are not uniform or maybe too low, resulting in parts with excessive sink marks or other defects. In volumetric shrinkage results, will show the effect of adding a pack hold time, which may reduce the sink mark or prevent internal voids in a part. And our pack holding time affects our part mass as well. More pack before the gate freeze off will push more plastic into the cavity, and we'll have more part mass there. Our clamp force result is going to be used to determine what size machine is needed to mold the part. So first we'll look at the effective packing time. There are a couple of ways to see when the gate's going to freeze off during the packing phase. One of these is by looking at the freezing time at post-filling end result. So this is going to allow you to use the ISO surface clipping mode, and I can put in a value. Basically, I just back up this wheel until I start getting a gap in there. So that's showing me that, okay, at this point, this is all frozen off and we're not touching the part anymore. So this means that my gate is basically froze off from the part and I can't make any more adjustments after that. So around 3.69 seconds, maybe 3.7 seconds, somewhere in there. So when my gate's going to freeze off. Another way is to see the gate freeze time is with our XY plot. So we can actually start an XY plot and look at a node temperature on our model. We have the option to set a reference plane. So this reference plane that I've got splitting down the center of my part, and then I can pick a point that's on that plane. So basically it's like section viewing my part. I pick a point around my gate and it's going to trace the node temperature through the cycle. So obviously when no material is at the gate, it's at a low temperature. Once the material hits the gate, then it's going to flow through it all the way through the fill side. And then once we get into the pack, our flow slows down. So it starts to solidify around there and we're packing under pressure. And once we get to the blue line here, which is our glass transition temperature of our material, we're once again around the 3.6, 3.7 second line on where that node is on my gate. So once again, we're right around that same area, but it's showing me, okay, at this point in time, basically my gate is freezing off. So our temperature at end of packing is another result to look at. It's going to show us where at the end of the packing phase, where the temperature is in the part. So once again, using the clipping plane option, I input the 170 degrees, which is the ejection temperature of my part, and I can see inside my part where if there's still areas that are above my eject temperature of the part. So this is going to allow me to look at that, make sure that those areas aren't behind where I would have ejector pins in my mold or things like that. In this case, the small blue area is probably not going to be a problem, but we can see those are a higher temperature. They're also in the same area behind where the sink marks for. So another thing where maybe we could change those rib thicknesses and improve this as well in the future. But when we look at our pressure at end of fill, in this case, in the previous case, we didn't have the gate and runner. In this one, we had the gate and runner. So we're hitting our maximum 100 megapascal limit that we have set in our settings. So another way to look at this is that when we look at our XY plot for our max inlet pressure, we can see the inlet pressure keeps increasing and then it hits that maximum limit that is set in our settings for the machine. And it's just going to level out at that 100. Once it hits there, it's just going to keep pushing at that. Basically, it's like rolling it almost into the packing phase before we get there. And then once it gets in the packing phase, typically you're dropping off the pressure and just holding this pressure. So we can't see the actual max that it took to fill this part. So that's one of the things we can change. I can go in and increase that in our settings. We can look at the packing pressure. So at the end of the packing phase, most of your part is expected to have a near zero pressure. We just want to make sure it's uniform across the part. You don't have any really high areas of pressure during the packing phase. So our volumetric shrinkage, I like to look at volumetric shrinkage on parts that have thick walls. Plastic materials are going to experience shrinkage in volume as they go through the phase change from liquid to solid. So high rates of shrinkage occur in areas of the plastic part that don't undergo a sufficient packing stage. A uniform shrinkage throughout the part is desirable. So if our range of volumetric shrinkage is relatively high for our design, if we have a really high range, it's probably due to a non-uniform thickness in our part. So we can actually change the part design, add some packing time. We can also look at mold design, packing pressure time, gate size, number of gates, and gate proximity to our high shrinkage areas. to actually increase the pack and reduce the volumetric shrinkage. So in this case, our volumetric shrinkage is over 7%, and I've got the clipping plane option set. And we're looking at the volumetric shrinkage in the internals in those areas that are the last to cool. And our volumetric shrinkage is around 3.25% for those. So we'll increase our packing hold time to see what effect that has on our volumetric shrinkage in our model. I want to increase my injection pressure limit to 150 megapascal so I can see where we max out. The fact that it did fill with 150 is probably plenty to see where we're going to max out on this part. And then I'm going to increase my injection pressure holding time to the 3.7 seconds that we determined that our gate is freezing off. So we're going to push as much material in there up until that point. But after I've increased my maximum injection pressure limit to 150 megapascal, our results now show that the absolute maximum was 118 megapascal. So it was just a little over that 100. So now we should be good to go with that. And our maximum volumetric shrinkage also, once again with the clipping plane option on, it's now, we have one little tiny area that's 3.1%. So everything is less than that 3.1%. Only thing over it now is in your runner system. Our part mass is also affected by the change in our pack holding time. So more materials packed into the part until our gate freezes off, which increases the density of the polymer, also increases your part weight. The difference can be seen in our analysis. This is the summary text file that gets put into the analysis as it's solving. So our difference in the analysis shows that it's just a slight difference, but our part mass before we added that few seconds of packing time, 20.82 grams, and afterwards we're 20.96. So it did push more material in there, and we can see that in the analysis. Our clamp force XY plot is going to help determine the maximum clamp force needed to keep our mold closed during the cycle. If the clamp force limit of a machine is exceeded, the pressure of the plastic is going to actually force the mold open, and then it will flash that parting line. So this could cause damage to the mold. So our clamp force is always going to be higher just after switching from the fill stage to the pack stage. You're going to get a more accurate clamp force prediction from that. So with plastic standard, you're only seeing the clamp force during the filling phase. So it's definitely, if you're going to utilize the study, you need to have Plastics Pro. Now we can look at the cool results. Cool results are part of Plastics Premium. It's going to simulate the cooling of our mold using a 3D CFD flow analysis of the coolant channels in the mold. We're going to explore the results of part cooling time, mold temperature, the coolant system pressure, and coolant velocities. So our part cooling time in the cooling analysis, we can calculate either by the eject temperature or by a specified cooling time. So the eject temperature method is going to run the simulation until 90% of my mesh elements have cooled below the eject temperature. And then the actual cooling time is unknown and isn't of the analysis. So we're predicting the cooling time that we would need to set on the machine, basically. If you specify the cooling time method where you know the cooling time, that simulation is going to run until the cooling time is equal to that value. That method is helpful when analyzing an existing process for optimizing my cycles. By using clipping plane option, we can also see the internal cooling times on our part. Same way as everything else, I can look at the cooling time, I can use the evaluate and measure and see what that actual time is in that area on the part. So my mold temperature end of cooling result, this is going to allow me to see the mold temperatures at the end of the cooling cycle. So once the cycle is finished and the mold is about to open, we can identify hot spots in the mold. We want to look for uniform cooling. Do we need to add more cooling channels or change temperatures? Our cycle averaged mold temperature is going to give us an average temperature of the mold throughout the entire cycle. So this average should be within the recommended mold temperatures for your polymer. It's also going to show you areas where the hot spots are on the mold, and we can look for non-uniform cooling of our part this way as well. So we want to make sure that we're cooling the same on both sides of the part. We don't have a non-uniform temperature on our wall of the mold. So we want to make sure to achieve the most consistent mold temperature on the mold surfaces to have uniform cooling. And then finally, looking at the pressure and velocity of the coolant system. The pressure of the coolant system is the static pressure distribution of the coolant flow as it flows through the cooling channel system. Our maximum value in this case is representing the pressure loss across the cooling channel, so we can see how much pressure drop we have. And then on the right hand side, we're looking at our velocity vectors, shows our flow velocity, and we can identify flow issues. Notice the little cross-drilled area down here. We can see that there's less flow in it because the fluid gets in there. It just kind of remains and doesn't flow a lot. But it's actually showing that, yes, the analysis is actually even solving for the little dead spots in your drilled holes. Finally, we're going to look at warp results. After running a warp analysis in SOLIDWORKS Plastics Premium, the displacement plots can be viewed. We're going to look at the displacement from the stresses that develop during the filling and packing and stresses because of thermal contraction after the part is fully cooled. We'll look at deformation displacement, part shrinkage, and then also how to create a SOLIDWORKS body from the deformed shape. So our overall displacement is going to show the total deformation of the part after it's molded and cooled down to whatever the ambient temperature is set in our system, your room temperature. All of your simulated stresses and thermal effects are considered in this result. Our directional displacement, we can look at in X, Y, and Z directions to display only the component of the direction. So it's useful for checking a displacement solution against a specified tolerance, and it's aligned with a global direction. So in this result, I'm looking at the XY plot. We're looking at the displacement in the Y direction. I'm able to pick nodes across the top of my part. And basically, it's like equivalent to measuring the flatness of my part. So I can see how much those nodes change during the cooling process. We can also use the measure tool under the evaluate and measure in SOLIDWORKS Plastics to measure the shrinkage values and see the displacement in certain areas of the part. So here we're measuring the shrinkage of the part in the X direction. The red and the blue boxes are showing the measure points on those nodes and the individual displacement for that node. So how much did that node move when the part finished shrinking? The magenta box is actually showing the difference between the red and the blue boxes. So it's taking how much both of those moved and combining that result. So that's giving you a prediction of the shrinkage in the X direction. We can use this value to actually calculate your mold cavity scale factor to compensate for shrinkage. And finally, our ability to create a SOLIDWORKS body or part file from the deformed shape. It's useful if you need to see how the deformed part will fit into an assembly. You can take that deformed part, see how holes align. If you have two mating parts, you can take those deformed mating parts and see how the faces fit together, those type of things. Our deformed model can be used to compare to the original part model prior to scaling up. So we can see where we are dimensionally based on the original part. And we also have an option where we can actually put in a negative scale value to reverse the warp. Then we can use that body to compensate for our mold shrinkage if we wanted to. So we can see I have a cover SD deformed part. So this is my molded part after it comes out of the machine, completely cool. So now I have a body that I can use. So that concludes my presentation, and you can email me at jlinderman@goengineer.com. If you have any questions or want to see anything else with SOLIDWORKS Plastics, please reach out. Thank you for watching. If you enjoyed this webinar, please subscribe and leave us a comment below with any topic you'd like us to cover in future webinars. Visit our website, GoEngineer.com, for access to professional training, upcoming events, and more from your #1 online technical resource. Take care.